Hello and welcome. We are starting our topic now on asymptotic notation. Let's just write this down. Asymptotic notation. Now, each of these videos in this series will probably not be super long because hopefully you've watched my other videos and you are now starting to feel a little bit more confident with respect to the arithmetic that you may have been having to do, with the logic and the proofs that you've been having to do. And now we're going to kind of bring it all together for us computer scientists. Now, a couple of things that we want to just remember is we're going to start by basically trying to understand the intuition behind why we want to do these things. And we want to do them so that we can classify different algorithms into different categories. And we're basically trying to figure out how fast different algorithms can run and which other algorithms we can compare them to. And when we look at a function like that is an algorithmic, that is sort of like a function of some number of steps, and we get something that looks like this, it's only so helpful, right? Like it's okay, but it's not great. And we have better ways that we can actually show things, as well as simpler ways for, especially for computer scientists. So for each of these examples, I will sort of go through the official definition of whatever the order of the function is that we're looking at, and then we will do the proof. So since we're talking about big O, let's make sure that we can first define big O. And so basically what we're saying is there's a function f of n, and it will be in the order of the functions in, we'll say, g of n, if and only if the following is true. So there must exist some m value greater than 0 and some n naught value greater than 0, such that for all n greater than n naught, f of n will be strictly less than or equal to, move all that over, m times g of n. So sometimes when we see things like g of n and f of n everywhere, and n naughts, and like all these like very mathy looking terms, we can often get a little bit confused and overwhelmed. But let's just remind ourselves that those are just like variables, just like anything else. Here in this question, right up here, we have an f of n and we have a g of n. We can pull those directly from equating it to this right here. Right, looks exactly the same. We have that in the setup. We have that O. It's exactly the same otherwise. So it's important for us to be able to sort of equate that back so that we can solve our problems and understand kind of what we're looking at. Now, what actually does big O mean? Pardon me, what does this whole thing here actually mean? Well, what we're saying is that this function n3 plus n plus 1, if we wanted to plot this on a graph, it would look like whatever it would look like. I have no idea. It doesn't matter. I mean, it matters, but I have no idea. But what does n to the 4 looks like? It looks something like this. Oh, that should have been more curvy than that. Something like that would be n to the 4. That's our g of n, and this one here is our f of n. And we're basically saying that there exists some point in time where we can say that this would be our point. Oh, crap. This right here will be our n naught. When we reach that point, that for all n's that are greater than that n naught, so all n's heading in this direction, and for all the m values that we might be able to multiply this by as it comes up higher, our f of n will always stay lower. This is supposed to be like this peters out. It's terrible drawing. But we're basically trying to find that upper bound. So let's just write that in plain English so that we don't forget what it means. So a function f of n is in the set of big O g of n functions if we can show there exists an n naught and an m greater than 0, such that all those n's greater than the n naught, and such that for all, sorry, that's where I lost that, for all of those greater than the n naught, our f of n, whatever it may be, will be less than or equal to our m times g of n. That's what we're trying to see. We're trying to find m, we're trying to show g of n set. Actually, it's not g of n set, it's big O g of n set. So O g of n function set is an upper bound to a function f of n. So given that's the definition of big O, and I'm telling you we need to find an m and an m naught such that that function is going to be true, we now understand that we need to take the things that we've been learning in the previous course, or in the previous weeks, pardon me, the previous units, to try and do this. So we've already defined our f of n like this. We've defined our m times g of n like this, m times g of n. And then we need to ask ourselves, what should those m and n naughts be so that we can make it work for all n greater than n naught? All right, so we can use our rounding up trick to try and solve this problem. We know that if we pick an n naught greater than 1, so we stay in that positive integer space, then we can say that 1 is going to be less than n, which is less than n squared, which is less than n cubed, which is less than n to the 4. So as long as n is greater than 1, those are things that we can say. Sorry, not if n not is greater than, if n is greater than 1, those are things that we can say. Now the problem space doesn't specify at this moment here how those values of m and n naught and n are necessarily defined, but in the original definition, f of n and g of n, so these two functions over here, are defined in terms of the integer, positive integer space. So that's just important to note so that we can use that if we need to. But again, there's no reason for us to find the tightest lower bound. The problem isn't even asking for that. So we can just recognize the fact that if we know that 1 is less than n to the 4, and n is less than n to the 4, and n cubed is less than n to the 4, we know that n3 plus n plus 1 will be less than n4 plus n4 plus n4. So we just rounded them all up until they matched what was on the right-hand side. So this is obviously true. Let's just label this as A and this is C. And we've now proven that A is less than our new statement B here. So B can also be rewritten as 3n to the 4. So now we're going to prove that 3n to the 4 is less than or equal to n to the 4. Well, if we let m equal 3, sorry, I lost that m there. If we let m equal 3 right here, we can very clearly figure out what our value of m should be. Divide both sides by n over 4. Sorry, not n over 4, n to the 4. And we can see that m needs to be greater than or equal to 3. So now we've been able to prove that our new found B is less than or equal to C. And so then we're able to now say that our A is less than or equal to C. Okay, so let's write this out a little bit nicer so that we have an actual formal proof here to follow along with. So by definition, what do we know? By definition, we know that n cubed plus n plus 1 is going to be in O of n to the 4 if and only if there exists, we're going to just rewrite that whole formula here, and not greater than 0 for all. let's just pull this down. Let's pull this down actually. There we go. For all n greater than n naught, such that n cubed plus n plus 1 is in that space of m n to the 4. So we take the values that we determined during our scrap work. We're going to let m equal 3, and we're going to let n naught equal 1. What this means is we will show that for all n greater than our n naught, which is 1, so for all n greater than 1, this will be true. N to the 3 plus n plus 1 is less than or equal to 3n to the 4. Okay, so pardon me, we have to sort of let n greater than 1 be arbitrary because it is a for all. So let's just say that. Let n greater than 1 be arbitrary because it can be any number in that number space. And if that's the case, then we can say that 1 is less than n squared, less than n cubed, etc. Right? And knowing that, it follows that n cubed plus n plus 1 is strictly less than n to the 4 plus n to the 4 plus n to the 4, because all I did was say that n to the 3 is definitely less than this one, n is less than this one, and 1 is less than this one. And as we just saw, that's definitely true for all of them. When we add all of that up, we end up with 3n to the 4, which is exactly what we said we were trying to prove up here. So we end up with that as needed. And that's all there is to it. So it's really not too bad to try and solve. So in the next video, we're going to do something similar. We're going to do another big O proof. So if you're looking for more examples, meet me over there for another exercise. Thanks and have a great rest of your day.